Okay, so last time we proved remark 3.4. What is a 3.4? It says if you have two functions fx, g of x, they are almost the same except x equal to a. So at x equal to a, uh, they may have different value, or possibly one has definition, one has no definition. I don't care, or we don't care. When this happens, then the limit fx and limit g of x are equal to each other if they both exist. Okay, so those two functions will have the limit together at a, or will have no limit together at a. Okay, so this remark again emphasizes that the limit of the function at one point is about the neighborhood, the information of the neighborhood of a, not the information of a itself. The function may have whatever definition at a, or even has no definition at a. Okay, so let's see the example of a remark 3.4, the example 3.5. Okay, prove that g of x cubed plus x squared minus x minus 1 over x squared minus 1. Prove that this function has a limit as x approaches 1. Okay, so first of all, we should notice that g of 1 is undefined because when x is equal to 1, the denominator is 0. So g of 1 is never defined. But we can try to simplify it and see what we will have. We simplify g of x as g of x. So the numerator, the first two terms, you factor out x squared, and last two terms, you factor out negative sign. Denominator is denominator, and the numerator again has two common factor x plus 1, so it's x squared minus 1 over x squared minus 1. And then you can cancel x squared minus 1, x squared minus 1 from top and bottom, you get x plus 1. But again, remember that whenever you cancel terms from top and bottom, make sure it is not 0. So this is correct only for x not equal to 1 and x not equal to negative 1. When x is 1 and negative 1, this is not an equality. Okay? Okay, so we're talking about the limit when x approaches 1, so it's around 1. So we don't pay attention to 1. So let's call it fx. Then the limit fx, this is a polynomial, it's very good, or linear function. The limit of fx is 2. So by remark 3.4, the limit g of x approaches 1 is also 2. So the limit exists. Okay, so we find the limit. Of course, the limit exists. Okay, so this is the example of the remark we just discussed and which we proved last time. And the next, we're going to get some connection between the limit of the functions and the limit of the sequences. We try to set up the connection between limits of function and the limits of sequence. Why do we need this connection? Because we already proved many results for the limit of the sequence. If the limit of function is strongly related to the limit of sequence, we can translate the result from sequence to the functions. Okay, so that's what we want, which is want to move some known result from sequence to functions. Okay, so theorem 3.6, which is called the sequential characterization of limit. Sequential characterization of limit. All right. Let A be real. Let I be an open interval that contains a neighborhood. And let f be a real function defined everywhere on I, on this neighborhood, except possibly at A. So may or may not be defined at A. Okay, then the relation is the following. L equal to the limit x approaches A f x. This exists even only if fxn approaches L as n approaches infinity for every sequence xn approaches xn inside this neighborhood excluding A that converges to A as n approaches infinity. So what does this mean? It looks very complex. This part is very complex. Actually, you consider xn as a sample point. Sample points converging to A. You have a sequence sample point converging to A. And for whatever sample point you select converging to A, you evaluate the function at the sample point, the value will approach A. If this works for whatever selection of sample point, then we will claim the function has the limit, the same limit at A. Okay, that's the meaning. Well, okay, let's prove. First, let's assume this function has a limit. Assume that the limit fx x approaches A is equal to L. Then by the definition, given epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus A is greater than 0, less than delta implies value fx minus L is less than epsilon. Okay, so that's it. Okay, so this is the limit of fx equal to L. Now we want to show that for every sequence xn converging to A, the limit fxn will be close to L. Okay, xn converges to A. We choose this delta as a rho of epsilon in the definition of xn converges to A. Okay, so for the same delta, for this same delta, there is an capital N in the set of natural numbers such that n greater than or equal to capital N implies xn minus A is less than delta. Okay, xn minus A is less than delta. This is the definition of xn converges to A. Okay, so let's read it. Now, for every epsilon greater than 0, there exists a capital N. Okay, so I've got copy this part, I copy this part, greater than 0. Capital N belong to the natural numbers such that for n greater than or equal to capital N, xn minus A is less than delta, this one. And this one implies fxn, now here is xn, here's x fx, here's xn fxn, minus L less than epsilon. Okay, so epsilon, capital N, n greater than capital N, the value is, the ups value of the difference is less than epsilon. So the limit fxn n approaches infinity is equal to L. Correct? So we use this delta as a little bridge to jump from epsilon to capital N, because epsilon is related to function value fx. Delta is related to x. Xn approaches A. Right? Okay, so this is our first part. When you have the limit of the function, you can get the limit of the sequence. Conversely, assume that fxn converges to L as n converges to infinity for all sequences xn in I converging to A. So whenever you have a sequence converging to A, then fxn will converge to L. Okay, that's good. Now we're going to show that function f, we need to show that the function fx, x approaches A, is equal to L, the same L. Well, we're going to prove it by contradiction. Assume not. Assume not. Assume not means, okay, this is for every epsilon, remember that. For every epsilon, there's a delta. Every epsilon, there's a delta such that whenever this, imply this. Okay? This is the limit. Now we're going to prove it by contradiction. We're going to say there exists epsilon greater than 0 for arbitrary delta greater than 0. For arbitrary delta greater than 0, so here, this arbitrary delta greater than 0, there's always this such that this condition actually for all. So there exists xn x delta with x delta minus A less than delta greater than 0, but it does not imply this. Fx delta minus L is greater than or equal to epsilon. You see, such that whenever means for all x with this condition. for all, when you put the contradiction, it means there exists x delta with this condition, and this implies it. When you get the negative, it does not imply that. So it has a greater than or equal to epsilon. Okay, so for every delta greater than 0, so choose delta be 1 over n. Choose delta be 1 over n. We're going to let delta become smaller and smaller. Delta be 1 over n. X delta is denoted as xn. X delta is denoted xn. And x delta, xn minus a is less than 1 over n. This implies the limit n approaches infinity, xn is equal to a. The distance between xn and a becomes smaller and smaller. So this limit is a. This limit is a, but we have a value of fxn here. Fxn minus l is greater than or equal to epsilon for all n in the natural numbers n. For all n in n. Right? For all n in n, then this implies the limit fxn n approaches infinity is not equal to L. Right? It's always away from L, so the limit is definitely not equal to L. It's a contradiction, right? This is a contradiction. The contradiction comes from your assumption. Assume the limit of the function does not is not equal to L. Hence, limit of fx, x approaches a, must be L. If it is not equal to L, we are going to construct a sequence converging to a, but the value of the sequence does not converge to L. Okay? So this is all possible. This is the connection between the limit of function and the limit of sequences. And here we want to emphasize this condition means for all sequence converging to A. It's not just for a family or for a large family, or whatever large, you have to cover all possible sequences. Okay? Also, this theorem gives us a way to show that some function has no limit at a certain point. How? It gives a way how we can construct two sequences converging to A, but the sequence of values f values. So you apply f to this sequence. The sequence of f values do not equal. Do not equal. So here you see in this theorem we say that fxn always converge to L for whatever sequence. If you have two sequences xn, yn, they both converge to A, but fxn converge to L1, fyn converge to L2, then the function will not be able to have a limit. Okay? So that's a byproduct. How do we prove some function has no limit? The characterization is about some function has limit, how function has a limit in terms of a sequence. Now let's see the some function has no limit at a certain point. prove that fx defined by sine 1 over x when x is not equal to 0. When x is equal to 0, just put 0 here. Okay, this is the so-called piecewise defined function. And this function has no limit as x approaches 0. As x approaches 0. Okay. How do we prove it? How do we show it? We are going to construct two sequences. Over one sequence, function has a limit 1 value. Over a different sequence, function has a different value. Okay, sine 1 over x. We know that sine what? Sine 2k pi plus pi over 2 is always equal to 1, right? Sine 2k pi over pi over 2 is always equal to 1. So let xn be 1 over 2n pi plus pi over 2. Xn be this. And then we know that f xn is a sine 1 over xn is a sine 2n pi plus pi over 2 is constant 1. And n approaches infinity. The limit xn approaching infinity is equal to 0. So this xn approaches to 0. That's good. And over this, you have a constant limit 1, a constant sequence 1, so the limit is equal to 1. Okay, so we get a 1. And of course, you get the other one, 2k pi minus pi over 2. This is equal to negative 1. So we define yn be 1 over 2n pi minus pi over 2. Then fyn is a sine 1 over yn is a sine 2n pi minus pi over 2 is equal to negative 1. And the limit of yn approaching infinity is also equal to 0. Okay, so you construct two sequences converging to the same point, but the function has different limit at those two sequences. Hence, fx has no limit at x equal to 0. If it has a limit at x equal to 0, these two values must be same. Right? So that's the proof. Of course, you can choose any other special values. You can choose this 2k pi plus pi over 4, that's the square root of 2 over 2, or 2k pi nk pi n pi sine n pi 0. Sine n pi is 0, so you will get the sequence of 0. Actually, there's so many different values. All right, so for different stuff, a different sequence, you have different value, then this function does not have a limit. Okay, and next we're going to move the theorems about the sequences to functions, limit of the functions. So here we introduce the algebra of functions. So what is algebra? Well, we say algebra. Algebra means you have a vector space with a scalar multiplication and a vector multiplication. vector space, sorry. This is redundant. Vector space means it has a scalar multiplication. A vector space with a vector multiplication, that's called an algebra. Okay? So vector space, linear structure, you have addition, scalar multiplication. So if suppose that fg, you have two functions, both defined over E with values in R, then for each x in E, we define f plus g, the sum of functions evaluate at x as a so-called pointwise addition. Here, because the values are in R, so you can do the addition. So this is well defined. Okay? And the scalar multiplication alpha f of a scalar alpha in R with f by alpha f, this is a new function evaluated at x, is defined to be the number alpha times fx. This is the product in the real numbers. So together with addition, scalar multiplication, you have a vector space. This is a vector space. And then we define the vector multiplication. Vector multiplication eventually will give us a vector. So the pointwise product, pointwise product fg of f and g by fg, new function, the product two functions, product two vectors evaluate at x is defined to be fx times gx. Okay? So this is an algebra. This is an algebra. Okay. And for the functions, especially in this current setting, we have additional one additional operation. It's called the pointwise quotient. Up to here, it's so-called the algebra. In the abstract algebra sense, here it's a algebra. And for the functions, we have a pointwise quotient. Pointwise quotient f over g of f and g by f over g, new function evaluated at x is equal to fx over gx. And here again, you put gx in the denominator, so gx is not equal to 0. For all x in E, you must have this condition. So it means this pointwise quotient is not defined for every function. It's only defined for some special functions, special non-vanishing functions, right? So it's not for all the functions. So that's why it's not part of the algebra definition. Okay, so after we define the addition, scalar multiplication, pointwise product, and the pointwise quotient, we are going to state the theorem 3.8. So suppose that A in R, that I is an open interval that contains a neighborhood, and that fg are real functions defined everywhere on I except possibly at A. Okay. If fx and gx converges as x approaches A, then so do f plus g sum of x, f times g product of x, alpha f scalar product of f, and f over g function of a quotient of x. So do them means they also have limit. They also converge, right? If f and g converge as x approaches A, then these addition, product, scalar multiplication, quotient, they also converge. In fact, the limit x approaches A, fx plus gx, the limit of the sum is a sum of the limit fx, x approaches A, plus the limit of gx, x approaches A, sum, scalar multiplication, x approaches A, alpha fx, alpha, limit x approaches A, fx. You can factor out the scalar coefficient. And the product, pointwise product fx gx, x approaches A, is a product the limit x approaches A fx times limit fx gx x approaches A. Limit product the limits, and the limit of the quotient of the limits. Okay, so again, whenever you have quotient, you have to make sure that the denominator is not equal to 0. If the denominator is equal to 0, there's no theorem you can apply. Okay, for example, here you have to assume g of x is not equal to 0 for all x in I, possibly except the A. And the limit g of x, x approaches A, is also not equal to 0. So whenever you see something in the denominator, it's not equal to 0. Okay? So how do we prove this? We just pass this to the sequences. You pick up sequences, you get the limit, because here, you see, fx, gx, they have the limit. fx, gx, they have limit. Then you can find whatever sequence xn converges, approaches A, then you have the fx plus gx equal to the sum of the limit. For whatever sequence, then you will transform back to the limit of the function. So this is exactly the sequential characterization of the limit. So we're not going to prove it. It's the theorem is very long, but it's very, very intuitive. So this is a direct application of sequential characterization of limits. Okay, so you start from fg, you pass it to the fxn gxn, and then you get the limit fxn plus gxn equal to something, and then you pass back to limit fx plus gx. So you have a middle step, xn. So x to xn, xn to x. Okay, so in the textbook, the author provide the proof for addition. You should be able to produce the proof, similar proof for the scalar multiplication, pointwise multiplication, and pointwise quotient. The same thing, almost identical stuff. All right. So you may see this type of proof in the exam. So try to do them, practice. So in the limit of the sequences, we also have another theorem, the squeeze theorem, right? So the limit of sequence has squeeze theorem. By the sequential characterization of a limit of function, we also have squeeze theorem for the functions. Okay, so that's a theorem 3.9. It's a squeeze theorem. For functions. Okay, suppose that A in R, that this is one condition, and second, I is an open interval that contains A, neighborhood, and that f, g, h are real functions defined everywhere on I except possibly at A. Okay, so that's a long assumption. We always write it because you have a point, you have a neighborhood, you have a function over the neighborhood, defined over the neighborhood except the point. It's a standard assumption. And then if gx less than or equal to hx less than or equal to fx for all x in I but possibly not at A, and the limit x approaches A, fx, this greatest function has a value L, limit L, x approaches A, the least function g has a limit L. Two extreme functions have the same limit L. Then two conclusions. First, the limit of middle term h of x exists. First, we claim it exists as x approaches A. And second, the limit h of x, x approaches A, is also equal to L. So there are two statements about the squeeze theorem. First statement is a confirmation about the existence of the limit for the middle function, and second is the prediction of the values of the limit for the middle functions. Okay, so there are two parts, and squeeze theorem is the theorem for the real valued function. Here it's very important, the real valued function. Why we emphasize its real value? It's because you compare numbers. Remember that if we have complex numbers, we don't have less than stuff. A complex number is less than another complex number. It is in general not making sense, right? So you can compare two numbers only for real numbers. Complex number, we don't compare them. We couldn't compare them. Okay, so this squeeze theorem is just a theorem for the real valued functions. Second, if g of x has ops value less than or equal to m, a bounded function, for all x in I, possibly not a, and fx converges to 0 as x approaches a, then the limit fx gx product x approaches a is equal to 0. Is equal to 0. Okay, so this part again, you apply the the limit of the square theorem for the sequence. You have x fx gx, you pass it to fxn gxn, you have the square theorem, you get hxn equal to L. And for arbitrary xn approaches A, then you get limit h of x is equal to L. Okay, so this proof is identical to the proof of a previous theorem 3.8. No difference at all. You only change the writing. In this one, the second part, remember the second part, g of x is bounded by m. So this fx g of x is going to be bounded by m fx negative m fx ups value. We have to put ups value. We will see it. So first, this is the first step. And fx approaches 0. Ups value of fx will also approach 0. So these two terms approach 0. Then by the square theorem, the middle term approaches 0. Okay? So this is the first thing. We show this one approaches 0. And then we apply the square theorem again. Arbitrary function, arbitrary number is bounded by its ups value and its negative ups value. So this one approaches 0, this approaches 0, this approaches 0. It squeezes the middle term approaches 0. Okay? So this is the proof. And here we have to put ups value. It's simply because if you do not put ups value, I don't know what is the direction of inequality. Because fx can be positive, can be negative. When multiplied by a negative number, you're going to change the direction. So it's bad, right? But anyway, with ups value, there's no problem. Okay, so this is a square theorem 3.9. 3.9. And except the square theorem, a weak version of square theorem is called the comparison theorem. Comparison theorem for functions. Okay, so we're going to have a similar long assumption. Suppose that A be real, that I is an open interval that contains A, and that f, g are real functions defined everywhere on I except possibly at A. Okay. Okay. So if f and g have a limit as x approaches A, and fx is less than or equal to gx for all x in the open interval I, but not possibly not at a. Okay. So here f and g have a limit. Here we don't say they have the same limit. Okay, just both of them have limit, and they have this relation. You only have two functions, not three functions. So that's why it's weaker. Then the limit fx x approaches a is less than or equal to the limit gx x approaches a. It's exactly the same result as a comparison theorem for the limit. Okay, so you pass this fx to the to xn fxn, you will have the same stuff. Cool. Okay, so 3.8, 3.9, 3.10, they are all direct application of a sequential characterization theorem. Sequential characterization for the limit. So there's no weird stuff. After we set up all these stuffs, we can evaluate limit easily. So we just get one trivial example and see it. So if we want to evaluate this limit, we evaluate the limit of x minus 1 through x plus 1, x approaches 1. We know that they are rational functions, a polynomial over polynomial. And we also know that the polynomial, they have the limit by the difference rule and the sum rule. And the denominator is never 0 when x is close to 1. And limit of the denominator is not 0. So you can try direct substitution. You let x be 0, x be 1 for the numerator and the denominator to directly have 0. And this is actually the limit laws, the difference rule and the coefficient rule, sum rule, and the quotient rule. Okay, so here, after all these laws, you do not need to go through epsilon and delta stuff. Okay, you don't have to go through epsilon and the delta stuff to prove it. But of course, if you want, you can try use epsilon delta to prove this simple one. It will be very complex, technically speaking. It will be very, very complex because you have to do the difference of two functions, the difference of two values and stuffs. It's not extremely simple. Okay, so we finished this section, the first section, 3.1. Let's see what exercise you can have. On page 63, the exercise 1, the exercise 2, and the exercise 3, 1, 2, 3, and exercise 4. Okay, let's just try them. 1, 2, 3, 4. Make sure you understand all the steps. If you have any questions, ask me. Okay, send me email. Thank you very much. We'll finish this video.